Our presentation block is for 40 minutes, and I would like to start with a brief introduction of our department. Our department has officially four groups, research groups, but practically we work in two teams. One team is focused more on production machines, processes, and robots. And another team, led by Professor Vidal, is focused more on control and related systems. I will start with team 37 to 50. It's a robotic team or machine tool team. We are focused on manufacturing processes, and we are operating the lower part of the stack. So that's something where are also origins of our research, and I will present more on that at the end of the session, our session. And the team led by Professor Vidal is focused, as I mentioned, on systems with time delay and active vibration suppression. As we can see here, for example, robots with additional bending device, or some also interesting industrial applications where the theory of the time delay system can be used. Colleagues have shared projects here, two projects from grant agency of the Czech Republic, and well, as a result from one of these projects, we will present today one of our presentations. So this is our plan. Now we will have 3 times 10 minutes for presentation of specific results. So now I would like to ask our colleague, Kuře, to present his presentation in the field of today.
Okay. Welcome. My name is Kuře, and I would like to talk about spectral design and experimental validation of non-collocated vibration suppression by delayed resonator and time delayed collision. At the beginning, let's discuss, or I would like to introduce you and explaining the difference between collocated and non-collocated vibration absorption. A collocated case, usually that's the first and typical tool to suppress vibration, where the absorber is directly attached to the target body, the primary structure. The design of the absorber can be passive only, or with the active control, we can achieve 0 vibrations. The advantage of collocated vibration suppression is that the absorber design, the parameters of the absorbers are independent of the primary structure, and the design in comparison with the non-collocated case is much simpler. But unfortunately, for people who want to suppress vibrations, fortunately for us, it's not always possible to mount the absorber at a place we want to. So, for example, there are few things, for example, at the tip of some tools or at the end of some manipulator. So, there is also a non-collocated vibration absorption. You can see where now we will talk about, we want to stop the body in one, and the absorber is located in a different part of the multi-body structure. And those positions are different, and as we can assume that the part of the body here in this example, the body M2 is used as a part of the substructure to suppress vibrations at the target body M1. That's the non-collocated case. It's much more difficult to design such a control because part of the body is used in the design. We also use part of the body to suppress the vibrations, so we should take care of fatigue in the structure. And what we need is quite precise model to develop good control. In our case, in this article, we focus on multi-body system with a parallel spring between body M0 and M1. And to briefly describe this body, there is a harmonic disturbance D coming from the right side. We want to stop it by the M1, and the absorber is the left. Typical procedure is to tune the absorber with the body M2, or tune it such that it becomes a resonating substructure, which counteracts the force coming from the body M0 to suppress the vibrations at the M1. But in this case, because there is a parallel link, it's impossible. So we have to use direct zero assignment at the transfer function from the disturbance D to the body M1, the displacement of the body M1. We use a space model with our output B, which is the displacement of the body M1, which we assume is not available. And there are two local input-output pairs, YC, UC, and YA, UA, which we use for suppression and stabilization. Our goal is to stop the body M1 from vibrating. The method we use is we use the concept of delayed resonator, which is quite a simple control law where we scale and delay our measured feedback. In our case, we use position feedback because from the implementation point of view, it's quite simple and easy to use. And our YA is the relative displacement of the body of the absorber and the body M2. As we discovered in simulations, when we tune when we set the absorber to assign the zeros, this method ensures that the zeros are assigned, but it does not ensure that the overall body is stable. So we have to check if the system is stable, and in case the system is not stable, we use secondary delayed output feedback controller. Again, while delay and position feedback, it was quite simple, yet powerful, and very well, like it suits very well for implementation. This becomes to an optimization task where the parameters GC and tau C are obtained from the spectral optimization of time-delayed systems. And for the optimization, we use the method package from colleagues of University of Leuven called Control. So far, we built our experimental setup on which we verified our control scheme. Composed of several mechanical cards. On each side, there are two base elements with brakes representing fixed frame. Cards are interconnected by springs, and the whole setup is instrumented by three voice motors, which are instrumented by custom-made control unit by controls. We measure the displacement for each card, despite the fact we assume that the position X1 is not available in the real setup, just to verify the performance of our control. And the position is measured by multiple magnetic strip with all colors of the relative position sensor. The whole setup is built on National Instrument Tools. It's implemented in LabVIEW and it runs on industrial controller. Here, specifically the Compactrio 94, which has several slots for inserting some modules, which extends the connectivity of the controller. Plus, it has integrated PTUing, which we use for sensor measurements. We achieved like good sampling for a control. We run our experiment at 1 kHz for control and data logging, and there is 48 MHz sampling for data acquisition, especially for reading and encoding the quadrature signal of the machine. I would like to show you the result, the video we achieved. We made 2 cases. The first case is for 4.5 Hz, in which the overall system is stable and there is no need to use additional stabilizing controller. Just to describe the setup, there is a disturbance. The voice call on the right is used to mimic the disturbance. Now, this voice call is used for delayed resonator to stop the vibrations, and as we can see, the card in the middle stops from vibrating. The voice call on the left is used for the additional stabilization controller, which was in use at that case. And there is a second case. You can see the video is for 7 Hz, where the system with the control was unstable, so we had to use the secondary controller to stabilize the setup. As we can see, we achieved no vibrations in the middle. From the practical point of view, we are limited by our voice calls, and from the experience I gained when I was testing this setup, those drivers, the control units are quite sketchy, so they are like very suitable for improvement. Additionally, because I think I'm running out of time, we had another publication done by my colleague and our team on stability optimization of time delay systems, where instead of delayed resonator output feedback controller is used, which was published recently in Mechanical Systems and Signals Processing. And at the moment, we are trying to extend our knowledge into several fields. First, as I said, non-collocated gates each part of the body of the structure. So there is a work currently undergoing on optimization of the structure to reduce the stress in the structure. And the second part is on tuning on the method how to tune the delayed resonator such that we can achieve better results for larger structures. I think that's it from my side. Thank you very much. Is there any question?
So I would like to continue with a presentation of the second paper we published last year. Now we will switch to the area of mechanical engineering. I would like to talk about spindles. Spindle is heart of the machine tool and significantly influences the machine process accuracy and productivity. I will talk about many spindles with many, so you can see here rotational tool for removing material. This is block of material. Of course, this tool should be carried and rotated and driven by something. So this is spindle, part of the machine tool that enables the tool can be clamped here and it rotates and there is enough power for the machine. And it's rotating system, therefore there are varying. In this case, angular ball bearings. And this is one critical part of the spindle and significantly influences accuracy and reliability of the spindle. The issue we have is that the designer at the beginning have to design, have to propose the appropriate size and type of the bearing. They use normally estimation of the spindle load. So this is a simplified graph of simplified distribution of loading of the spindle, various solutions and various torques, and using this formula here. Sorry, it isn't well visible here. It's possible to calculate lifetime of the bearing, and for normal application, it should be about 12,000 hours. But in the reality, of course, every machine with the spindle can be used for different operations, so we can have completely different distribution of the load. So you can see there are much more combinations, and they have also a smaller time portion on the total operational time. So the idea for estimation of the remaining useful lifetime of the spindle is to monitor the realistic reload and online recalculate the lifetime of the bearing. So how it works? At the beginning, we use the whole machine tool as a sensor. So we read data from the drives, from the foot axis, XYZ, and also from the spindle. And we have a simplified geometric model of the spindle. It's just being into bearings, and a simplified model of the tool, and using geometrical dimensions here, we can calculate approximately reactions in bearings. We also monitor the distribution, time distribution of the load revolutions, and these are inputs into one formula for recalculation of the total lifetime of the spindle bearing. And then just these results minus already total operating hours, we get as a result an estimation of lifetime of the spindle. So this is example how the results can look like. This is estimated remaining useful lifetime, and here we have operational hours of the spindle bearing, and we can see, because the calculation is done in discrete time points. These discrete time points can be, for example, 1 month, once a month. So we can see that the remaining useful lifetime is decreasing because there was, for example, a high load on the spindle. Then it can be stable, or it can be even increasing trend, because it means that during this period probably the spindle was not loaded so much. Well, this is valid just for loading and possible damaging of the spindle due to external load. But spindle can be damaged also with external influences, for example, moisture inside bearings can affect the lifetime of the bearings and so on. Therefore, we saw that it is necessary to correct these results with the real signal of the vibration of the bearing. So therefore, there is some cubic correction result, and we can see this. Sorry, this is case. If you have constant load of the spindle, we can see that the remaining useful lifetime is decreasing constantly. But if there is another type of the damage on the spindle, using the correction from the vibration, we can see that the estimation is going down. Well, so these are all the illustrative pictures. What we did, because the question was, can we, by some automatic system, have some algorithm that would check the condition of the spindle instead of the human skilled, human technician. Advantage of this method is completely automatic operation. However, there are some limits. So what we did was contain the comparison between the algorithms and between the skills diagnostic guy. We use data from the production. The guy used, say, usual offline diagnostic tools. We had two groups of spindles, so two design types, and for every design type, we have 3 pieces of the spindle. So here is comparison of the estimation of the remaining useful lifetime done by the expert, the diagnostic guy, and by our system. You can see that there is not a match. Just this case was completely out. So this was a very simple validation of how such system can work in comparison to the skilled expert. So that was about the remaining lifetime of the spindles. I don't know if have time for one question. There are not. I would like to invite Jan Koubek for the last technical presentation within this blog. This is presentation of our applied result within the project Competence.
Thank you for the introduction. The main partner in our project is the company Laserdown, a manufacturer of automatic welding cells and laser solutions. Now the problem description. The main problem in the welded structure is stiffness, steel stiffness and position accuracy. In the detailed image, you can see the ideal edge position in blue. The real shape of the part is deformed, and edge position is marked in red. So, solution design or method of predeformation of robot tool mainly consists of metrology inspection, metrology on the tvar and on robot or product cell. When we load data into our scripts in Siemens and its development software, then we make one or post-processing, and the data go to the next step of the validation. Workpiece correction procedure. We have problem with weld B, position error, deformate system, and ideal part. We optimize the ideal part through the error model and minimize the position error for weld B's by using 0-point shift. And regular predeformation on the part. Industrial application and validation. So we solve identification of the master geometry at the workstation and workpiece errors. It's a goal or task. We compare the workpiece errors and find suitable solutions procedure. And main results and advantages of the method is the topic. The development complex model allows to design a welding procedure of the whole system in order to achieve an required tolerance of the weld form position with maximum deviation the trajectory of plus minus 1 millimeter. Potential time reduction from 100 hours now is only 20 hours in the validation case. Thank you for your attention.
Last technical presentation. I have here last slide from our local presentation. I would like to mention again, we are responsible for the lower part of the testbed. We have equipment there based on machine tools and robots for various types of the processes, which is quite interesting because we have machine tools, robots, the devices for different types of processes, for example, subtractive processing, machine or additive processing. I would like to say that these are our main machines. We have full equipment for machine processes. This is the main machine here. Also digital twin. Physical based digital twin, so we are able to run also quite big volume of simulations of the whole process. Then we are focused on laser processes. Our laser processes, this machine robot with laser cutting head. Then large scale plastic additive manufacturing. This is this robot with pellet extrusion and milling robot. So there are another type of programs we have to solve because machine with programs is completely different story as machine with machine tools. And this machine tool is a machine also for hybrid production, so it combines in one working space by machine. We have also equipment for tool presetting, for measurement, workpieces, quality assurance, workpieces, and so on. I wanted to mention these devices are involved as well. Please do not hesitate to contact me if you would like to see how it works, because I think there are quite interesting areas that we will share in control, and also in the presentations I saw here about the table definition of C. That can be also very well right here. So all of you are invited in our laboratory. We can share this nice playground. So that was all for it. I don't know if there are some questions. So thank you for your attention, and this is the last one.